Let's talk about special relativity. One of the four things that Einstein came up with in his miracle year, 1905. In 1905, Einstein released four papers. And the one he got the Nobel Prize for, it was the explanation of the photoelectric effect. It explained why photography works. How we get these images just by opening up, a little, whatever you call those lens things that open up slightly, aperture, and then it lets a little bit of light in, opens and closes real quick, and then that little bit of light hits some film, and now you've got an exposure. Certain properties of the film mean the light leaves an image of what was in its field of view. And photography had been around for a while then, but nobody really understood exactly what was going on there, how it worked. Einstein figured it out. He called it the photoelectric effect, and he explained that photons, light, when you let it in like that and hits that substance, hits the electrons on the film, and the energy of the light, depending on the frequency, knocks out electrons, knocks them off the surface of the film, causing an image to be left. And how the whiter the light, the stronger the frequency, and therefore it would knock out more electrons and leave a lighter image on the film. And that's what was going on in black and white photography anyway. And so and by explaining this, he helped it, and to get there, and in that paper he explained the quantum nature of light, that it comes in discrete packets, and those discrete packets contain a finite amount of energy, and when the energy is enough, it hits electron, it will have an effect. And then what else did he come up with that year? Brownian motion, which led to the atom. He noticed some dust in water, in a glass of water. He noticed some dust in there, and he noticed that it wasn't staying still. It's kind of moving around a little bit, ever so slightly. Why? It was no wind, nothing at all. Molecules is why. And that led, to the atoms had already been postulated by then, but most of the physics world was reluctant to accept that. And that sort of locked up the case for that, the atom. And then, what else? He came up with the Special Relativity was another paper, and then something emanating from that, mass energy equivalence, E equals mc squared, was another separate paper. All in 1 year. And these things, these four papers, and the atom one gave us quantum mechanics. These four papers today are the foundation of all of modern physics. Einstein's paper, quantum mechanics and the photoelectric effect, and then relativity from the Special Relativity in 1905. And then in 1915, he came up with another paper on general relativity, which explained that gravity, the force of gravity, is really just the curvature of space, and it's not a force emanating from massive objects. Einstein deserves everything that he gets in terms of, recognition, even posthumously from that. But let's look into special relativity a little bit. It's really a fascinating thing. And I would say that the vast majority of people who took physics in college, and even got an A in the class, maybe not necessarily those who, got degrees in physics, but I would go as far as to say that even a lot of those people don't really understand what space-time is and the special theory of relativity. So let's jump. What don't they understand? What do I get that they don't get? Okay. So space-time, after Einstein, it ceased being called space or time in the physics realm. It's space-time. And one thing, They're the same thing. And that's what's important to understand. They're the same thing. Space and time are interwoven in a way that you cannot separate them. Now, let's look at that. When we think of special relativity, we often think of the speed of light. Now, the speed of light is kind of a misnomer because the speed of light is just a consequence of what's really going on. The underlying thing is a constant that we have. And that constant causes things to travel, which have no mass at all, no rest mass. Let me clarify that. No rest mass. What does rest mass mean? Well, light, for example, the photon has no rest mass. That means if you could stop it, you can't. It always moves at one speed, the constant, which is about 300 million kilometers per second. Is that right? 300,000 kilometers per second, 300 million meters per second because of kilometers and thousand meters. So yes, so it's 300,000 kilometers a second. From our perspective, not from light's perspective. Another important thing to understand. From light's perspective, everything is instant. There is no time. There is no time. Why is there no time for light? Because light is moving through space-time at the full speed, maximum speed, through the space part of the dimension. Light is moving at c, the maximum speed in the universe, the only speed for anything without mass. And everything is instant because it doesn't go through the time dimension at all. It's using all of c, the constant, in the space dimension. Now, if it were to use any time dimension, it would have to take away from space, because c is the maximum speed you can travel through space-time. If you're traveling through time at all, and that's what you need to do to experience any time, then you necessarily take away from the space speed, because there's a maximum speed. And so here's the equation: s for space plus t for time equals c. So if you're going to maximum through space, you don't have any left for time. You're going the maximum speed. Any time that you experience would necessarily take away from space. And the reverse is true also. We go through space-time at light speed, in a sense, through the time dimension. If we start to move through space at all, we take away from the time dimension. Now, when we're walking down the street, the effect is so negligible, 0.0, that it doesn't, really subtract from our time. But it does, to some degree, just a very, very, very tiny amount. So when we get in our rocket ship and travel, if we could travel at near the speed of light, you probably hear this, the closer you get to the speed of light traveling, then time slows down. Well, it doesn't slow down, it speeds up. It doesn't change for you, because you're in your local reference frame. For you, time and space and time are always going to be the same thing from your particular reference. It's other people looking at you that aren't going fast that are going to see, just like light. If we watch, we say light years. It takes this many light years to travel from this star to us. So that if that star is 10 light years away, then it takes light 10 years to get to us. But not for light. It was instant for light. So here's the thing. It's what relativity means and why he used that word is that time and space are relative to the observer. When we look at light, that's how long we see it traveling. That's from our perspective. From light's perspective, it's instant. There is no time because it's using all its maximum speed in the space realm. It doesn't use any in time, so it doesn't experience time. It's instant. If you could travel at the speed of light, something 1,000 light years away would still be instant. You will be there in less than a second because you don't experience time, and you need time to have increments. You can't. Traveling doesn't take any time if you don't experience time. You know, time allows us to have this event happen, followed by this event, followed by that event. Without time, there are no events. For light that was emanated from the Big Bang, which I don't really believe in the Big Bang, but light that was emanated that long ago, to the light, from the perspective of light, of course, it's not conscious, so it doesn't think anything. In order to have consciousness, you also need to have time, you know, otherwise you can't think of something and then think of something else. So for light though, that was emanated 13.7 billion years ago, it's still the Big Bang. No time has passed because it doesn't experience time. I don't know how, you know, I'm sorry that I keep repeating that. I just want to hammer that in. Okay. So, now for us, we experience time. And therefore, when we look at light, we see time. It takes, on our field of vision, that's the speed that it goes. And our view of the space around us is based on this C, this maximum speed. So the maximum we can see anything go is the speed of light. So it doesn't matter that light is traveling instantly from point A to point B across space-time and that it doesn't see anything. We have a speed limit because of the time. We can only see light traveling at a maximum speed of that time limit. Anything. And so that's the speed that we watch it go across space-time. Okay, so S plus T, space plus time, has to equal C. And we're going through time at the same speed that the light is going through space. So by the same token, so we're light speed through time, which means we experience the maximum amount of time. We can't make time slow down. We can only make it speed up from our perception relative to someone else's, or rather just another observer's. So these things are all relative. For light's instant to it, you know, but to us, it goes at 300,000 kilometers a second. And we're not moving through space. And even when we're flying in our fastest rocket or, you know, plane or whatever, the fastest that we can propel ourselves to go, it's still not even a fraction, you know, of 1,000th of 1% of the speed of light. And, you know, so it has a negligible effect. But an effect that we can measure. And so we've, you know, Einstein's theories have been validated probably more than anything else in other theories out there. Everything we test just further substantiates that this dude was on the money. And this is what I think a lot of, you know, I think, you know, they teach in physics class a lot of the esoteric, you know, things about light, and people find it fascinating. Oh, you could go back in time if you could travel faster than the speed of light. If the speed of light means no time passes, then faster than that would, but there's no, you know, it's not, you can't go faster because that's like a hard rule written in. It's the whole reason light goes that speed. It would go faster if there was possible to go faster. It it's untethered from the Higgs boson, which gives mass, imparts mass to particles. And because it's untethered from it, it goes at an infinite speed. It's really infinite. Light goes at an infinite speed. But to us, it is not infinite, because we are mired in this molasses called the Higgs field that imparts mass to particles. And in that molasses, we experience time. And nothing is infinite or timeless when you're inside that field. And so that's what's going on with special relativity. That's what's going on with space-time.